This is fundamental problem 7 from chapter 18. If the 30 kilogram disk is released from rest when theta is equal to 0 degrees, determine its angular velocity when theta is equal to 90 degrees. So we're going to use the work energy conservation law. In this problem, I have T1 plus V1 plus the work done by non-conservative forces, which should be 0 in this section, is equal to T2 plus V2. The disk is starting from rest, so T1 is equal to 0. I also need the change in gravitational potential energy. There are no springs in this problem, so I don't have any elastic potential energy. I start at an angle of 30 degrees and I end at an angle of 90 degrees. So what did I say? I started at an angle of 0 degrees. So initially, the disk is like this. The angle is 0 there. And finally, the disk is like this. So I want to find how the height changes. Well, if we go from here to, that would be like down here. So that change in height is just equal to the radius of the disk. And the change in gravitational potential energy is negative since you're ending at a lower height. The change in height is 0.3 meters, which is the radius of the disk. Then I need the final kinetic energy. You have two choices for the final kinetic energy. You can use equation 18.6 or equation 18.7. Remember that equation 18.7, you can also say this moment of inertia is the moment of inertia about O when you have a pin at point O, and O would also be the instantaneous center of zero velocity in that case. So rather than using equation 18.6, we're going to say this is equal to 1/2 times the moment of inertia about 0.0 times the angular velocity squared. So now I have to go to the back of the book. And for the moment of inertia for the thin circular disk, they give me the moment of inertia about the center of mass, but they also give me the moment of inertia about an axis which is passing through the outer rim of the disk. So I'm going to use that. So my moment of inertia is 3/2 times the mass times the radius squared. That's assuming that pin O is right on the outside of the disk. I know the mass is 30, so this becomes 3/4 times 30. The radius is 0.3 times omega squared. For the forces acting on the disk, I have the force of gravity, and we did gravitational potential energy for that. The only other force I have would be at pin O, and they do not do any work. And so I can say from this equation here, T1 is equal to 0. This is equal to T2, which is 3/4 times 30 times 0.3 squared times omega squared minus mg times 0.3 for the change in gravitational potential energy. The mass is given to you, that's 30. And then you can solve for omega, and you should get 6.60 radians per second for omega.